Okay, let me share it again. Okay. Good. Okay. All right, so now let's keep going. Let's do another example. So here's an example of a linear function. Just make sure am I recording? Yes, I am. Good, good. Okay. So we have f of x equals 4x minus, press the wrong button. 4 times x minus 8. Okay. And what we're going to do here is we're going to confirm the rate of change is 4. In other words, we're just going to calculate the slope. But I'm actually going to show you also that if you increase x by 1, the function value is going to increase by 4. But really, again, it's just calculating the slope. So for instance, let's say x was 0, okay? So 0 I chose arbitrarily. You could choose any number you want. But if I get f of 0, well, that's just negative 8, right? So we get this. So that's a point on the line. Now, if I increase x by 1, that is, if I consider when x is 1, f of 1, right? That's what we're calculating. By direct calculation, we get this. And this is, of course, 4 minus 8, which is minus 4. But notice here that if you increase x by 1, the y values, the second coordinates, they're increasing by 4. Negative 8 plus 4 is negative 4. Or you can also calculate the slope. That's what I'm doing here. The slope is 4. I mean, you probably could tell also by just looking at the equation, but this kind of confirms it. For these two examples, at least. Okay, that's good. That's one example. Now, you can use any 2 points you want to calculate the slope. So you could do this if you want, but you can use any 2 points. For instance, what if I use negative 1? Okay, when x is negative 1, by direct calculation, I have this. And then when x is 2, 2 also I chose randomly. You know, you get f of 2 is 0. But if you were to calculate the slope, change in y over corresponding change in x, you get 4, right? I mean, I know you could do rise over run. I think people do that. But really, again, it's just change in y over corresponding change in x. That's all it boils down to. Okay, good. That's fun. Okay, okay, so we have that. Let me move on to another example. So now we're going to look at lines. Let's find an equation of a line through these 2 points. Okay. So we want to find the equation of a line. Well, if you want to get a line, you definitely need the slope. You know, the slope is something you have to calculate. Okay, so let's do that. So we have our 2 points. What do? Just change in y over corresponding change in x. That's what we're doing, right? 7 minus 3 over 3 minus 1. See? Change in y, corresponding change in x. Change in y, corresponding change in x. We get 4 over 2, 2. So the slope is 2. And this is actually one advantage of that point slope form that I had before. Actually, you know what? Let me go back to it. I can get to it. 1 second, I'll find it. But here, once you know the slope, you can use any point on the line for your point AC. You can do that. You have y minus c is m times x minus a. So you could do that if you want. And that's what I'm doing over here. In this case, I'm using 3, 7. We have y minus the y coordinate, 7, is 2 times the slope times x minus the x coordinate. Now, if you don't like that, You could use the other point. So here we have our y and x coordinate, same thing over here. But you might be confused by this. If you are, that's okay. You could still use the mx plus b form. That's fine. You can use the mx plus b form, but notice though, we don't know what b is, right? So we could use this form. We don't know what our b is, right? We don't know what happens when x is 0. But what do we do then? We can find it. In other words, we can use either point to find it. Because both points here, they're on the line, both of these have to be solutions to this equation. They have to satisfy this equation. And we can use that to figure out what our b is. So we can use we can use either point to get b. So what I did was I used 1, 3, as you can see here. So when I replace x with 1 and y with 3, the equation has to be true. The equation here has to hold. Equality has to hold because this is on the line. So now we have an equation where b is our unknown. We just solve for it. Right? We have 3 is 2 times 1, right, plus b. And 2 times 1, of course, is 2. So we just solve for b, right? We want b all alone. So we subtract 2 from each side. We get 1. And b now is alone, so we get b is 1. So we have y equals 2x plus b, but we got b is 1, so this is our line. This is our line. So the slope is 2, meaning the rate of change is 2. Okay, well, it's fun to graph this. If we were to graph it, we would get this. We would get this. Now, what do you notice about the line? Well, it's increasing. How do we know it's increasing? Well, again, if you move horizontally to the right, what is the graph doing? It's going up, going up. See? It's rising. It's climbing. This is increasing. We could have seen that without graphing it by looking at the slope. In other words, since the slope here, 2, is positive, that alone tells us the function is increasing. What am I saying? I'm saying this slide, that if you have a linear function whose slope or rate of change is positive, then the function has to be increasing. I mean, if you think about what rate of change is, you would expect that, right? Because if you increase x by 1, your m being positive tells you the output has to go up. Your output has to go up. That's if your slope is positive. If it was negative, it would be decreasing. And that also makes sense, right? Because if you increase x by a unit, your function, right, your y, is going to decrease by m. It's going to change by m, but if m is negative, it's going to decrease. That's fun. And if m happens to be 0, right, well, then this thing is gone. F of x is always b, and you get this. So these are just ways you can tell if a linear function is increasing, decreasing, or constant. I mean, not every function you can tell without graphing, but this function you can tell immediately without graphing. Okay, that's good. Now, okay, so I have some backup examples I think we should do. Let me just pause the recording though.